welcome back. I apologize for the technical difficulties, but yeah, so let's go ahead and move on. If y'all want the link to the video, there's the link. And yeah, we're recording the review. So this week we talked mainly, or last week, y'all had your test and then y'all did SN2 reactions, right? So I mainly have a bunch of SN2 reactions just to work through first, and then we'll just rank trends for SN2 reactions. And then I made a synthesis question, which is always fun. Y'all haven't done synthesis before, but y'all now have enough to start thinking about what it means to synthesize stuff. So before we do SN2, before we do that reaction, let me explain how an SN2 happens. So let's say I have a carbon attached to three things. Okay, so I've got a carbon and it's attached to three different things. Let's call this H1, H2, H3, and I have a leaving group. What's a good leaving group for SN2?
Any halides?
Any halides, so let's do iodine. Okay. And then I'm going to attack with, let's see, nucleophile. Okay, what's an example of a nucleophile I could use for SN2?
So anything except H2O and OH. Like
Yes and no. So there's a lot of different nucleophiles I can use. It's not anything, and I think your textbook has like a list. Your slides at least have like a list of good ones. But I can use like cyanide. I can use N3. There's a lot of different things. Let's use N3. So I have N3. Hold on. Okay, and then it's gonna go. Okay, and it's gonna come and it's gonna backside attack, right? That causes the iodine to leave, and I basically get. So when it's doing that, I'm gonna draw the transition state. Okay. So basically, I get this: H1, H2, H3, and the iodine bond is breaking with the carbon, and my nitrogen bond is forming with the carbon. Okay? This is what we call the transition state. Okay? And after this happens, I get inversion of stereochemistry. Right? So now I look like this. H1, H2, H3, and 3. Okay? So we inverse stereochemistry. You see how this used to that. The group that I'm removing used to be on top, and now it's on the bottom. That's what we call inversion of stereochemistry. Okay, so I inverse stereochemistry, and this is also this is bimolecular. One step. Okay, so, and that actually reflects in the name. SN2 bimolecular. And what we mean by bimolecular is I have two different things that are reacting in its rate determining step. I have two separate things that are coming together. And you guys will learn different reactions that will have, you guys will also learn something called SN1, and that's uni. That's not uni. Unimolecular. So that's the difference. And the S means substitution. Right? It means that I'm taking my iodine and I'm replacing it with something else. Okay? So, the big things, inversion of stereochemistry, bimolecular, and one step. Okay? And so, all we need to do is take our nucleophile and our leaving group, and we need to swap them. Okay? So for this one, what is my bromine? What do I call the bromine? This is called the leaving group. And what is sodium methoxide called?
So sodium is positive, so oxygen is negative.
Okay,
So
perfect.
negative will be the nucleophile.
Yes, so I'm going to get this is going to be my nucleophile. Okay, so the negative charge is going to come attack the bromine, and this is what we call backside attack.
So it attacks the carbon, which is partially positive.
Yes, so what's happening is, that's a great point, right? So the bromine is pulling electrons away, so the carbon is partially positive. And what that means is the carbon is primed for backside attack, okay? And so when I backside attack, what that means is I invert stereochemistry. So here it doesn't really matter because I don't specify what stereochemistry it is, and also that's not a chiral carbon, right? It's not a chiral carbon, so it doesn't matter as much. But basically what happens is my product is this, OCH3. All I did was I substituted my leaving group for the nucleophile. And that's all that is. Questions about how I got there? Alright, so let's move on to the next one. So here I have stereochemistry. So let's make a couple notes. Here I have stereochemistry. Okay, so here again I have KOH, right? And what that means is I have that positive charge on my potassium and a negative charge on my oxygen. And again, I'm going to backside attack. Okay, so when that happens, what I get is big thing to note, switch from from wedge to dash. Always change stereochemistry. Okay? SN2 always changes stereochemistry. So I have a dash, I'm going to switch to a wedge. You have a wedge, I'm going to switch to a dash. But when I do SN2, it always switches. Alright? So, questions or comments? Alright, cool. So, what I'm going to do is let's jump ahead to the ranking questions, and then let's do the synthesis, and then if you want to continue doing these kind of questions, let's do this. But this is pretty simple, so let's move on. And then if we have time, let's come backwards. Okay.
The fourth one, it has 2 oxygens. Does it matter?
No, because only one of the oxygens are going to attack. Yeah. Do you want to do this one?
Yes.
Okay, perfect. All right, so I have CH3Cl, which is basically a carbon with 3 hydrogens and a chlorine, right? And this is going to attack. Okay, so it's the potassium and the oxygen that have the charges. So I get positive charge on the potassium, negative charge on the oxygen, okay? Same thing, same as usual. This oxygen is going to come attack, backside. Whoa, what was that? Okay, it's going to, same thing, okay? It's going to backside attack the carbon, backside attack the carbon, and it's going to kick off the chlorine, okay? Now what that gives me is I know that looks kind of weird, right? Usually we think the nucleophile is going to be smaller than the substrate, but in this case, it's actually bigger. That's all that's going to happen. And this is actually not that great of a nucleophile. I just wanted it to kind of just practice and play with like substrates and nucleophiles look very different sometimes.
So except the potassium, all of it will go ahead and
Yes, yes. Because remember, the oxygen and the potassium is ionic bond, right?
yes.
So it breaks apart. All right, questions, comments? Ready to move on? Perfect. All right, so let's talk about SN2 reactivity. Okay, so we're talking about alkyl halides. Alkyl halides, okay? And so basically, we're just talking about the ability for the leaving group to leave, and also the substrate to be able to become backside attacked, right? So 1, leaving group, 2, ability to be backside attacked. Okay, so when we think about this, methyl is going to be better than primary, better than secondary, and it's way better than tertiary. This is very bad. I can't spell very. Very bad. Basically never happened. Remember when we talked about iodine and how like you can, how like iodine, it will basically never do halogenation even though it technically does it like very slowly. Same concept. A tertiary basically doesn't have it. If you see a tertiary, just don't do SN2 because you'll just get it wrong, guaranteed, okay? So never do SN2 for tertiary, but you're going to favor a methoxide, and the reason why, or a methyl, and the reason why is we consider something called sterics, okay? And so, let's think of it this way, okay? So this carbon is a carbon attached to a hydrogen, attached to a hydrogen, attached to a hydrogen to a bromine. So that's actually pretty ready and pretty easy to attack, right? Those hydrogens are tiny, there's a lot of space. All right, now look at this one, okay? This carbon is attached to an iodine, attached to a carbon, attached to a hydrogen, attached to a hydrogen, attached to a hydrogen, attached to a carbon, attached to a hydrogen, attached to another hydrogen, another one, and I have another hydrogen. So these methyl groups are these big things that are making it harder to attack that carbon, right? Think of it as you're an archer. The nucleophile is like an archer, and it's trying to hit the target. If you have a bunch of trees that are kind of blocking the view, it's going to make it much harder to hit that target, right? All right, how about this one? This carbon is only secondary, right? This is secondary. But next to it, I have these groups. So again, there's sterics involved that once again makes it harder to hit, okay? This one is tertiary, so it's going to be very sad. And then here we have a primary, right? So again, I have all these hydrogens, but it's going to be less than this one. Does that make sense? Yes.
Why is that one secondary?
Which one?
The one with the HO for us, for S.
I'm so dumb. That's primary. I'm sorry. Yes. Good catch. Good catch. Yes, it is primary.
Okay.
Yes, that is primary. Questions about this? All right, something else to consider. So not just sterics, we also need to consider polarizability. And not all of these are going to be, not all these concepts are going to be in this question, but just things to consider. Polarizability, okay? Which means the ability for the iodine. So iodine is the most polarizable because it can move its electrons around, which makes it even better for SN2. Because when you look backwards at this, right? The iodine here, it can change its shape a lot better. And because it can like shift its shape, it makes it a lot better for SN2. Something else to consider is how partially positive your carbon is. So if you're next to a much more electronegative atom, it's going to make it a lot better. So my leaving group, if it's more electronegative, it's going to cause a more partial positive carbon, which is going to stabilize my SN2 reaction and speed it up. So, based on that, let's think through which substrate will be my best one.
The one because of the CH3,
The one on the left?
the CH3Br,
Yes. And why is that the best one?
because it's not crowded by the metal, that's only one metal.
Yes.
They're attached to it.
Yeah, so this has no methyls. So that's good. Okay. This is going to be a last one. This is tertiary, so bad. Okay. And now I have a couple more to consider. I have a primary that just has a bromine. I have a primary with next to a tert butyl, and then I have a secondary. Okay, so I know automatically this is gonna be number 2 because that one's better than either of them.
Yes.
I'm gonna say this one's 3 and this one's 4. Big-
Why is this?
Because first of all, I have an iodine, which makes it very polarizable, which automatically makes it better. Well, not automatically, but that's pretty good. So that's in its favor. But usually when you have a quaternary, this is called a quaternary carbon. If I'm next to a quaternary, that's not very good. And so it's going to make it very, very, very difficult to happen.
So if this HO4S would be next to just like a structure like with no quaternary, so then it would be much more better because
Yes,
it's
this would be
close
better.
to electronegative.
yes, this is better. But this is not good because it's mainly because of this quaternary zone.
Okay, got it.
Question about how I did this? Comments? Okay, cool. Moving on. Let's do the next ranking. Okay, so now we're ranking nucleophiles. And what we care about for nucleophiles is we want it to be small. And we want it to be electronegative. We want it to be not a strong base. We also want a negative charge. A negative charge is always better. Yeah. So those are things. So the reason why we don't want it to be a strong base is because we want it to go start pulling off hydrogens, right? We would much rather it SN2 attack than pull off hydrogens. And so based on that, remember we did the bean chart for acidity rankings. It goes like this: carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, iodine, B, E, A. N is nucleophile.
It increases down the group.
Yeah, so it goes this way. Nucleophile is on the bean chart, okay? So what is going to be my least nucleophilic atom? My least nucleophilic atom. So the one furthest away from the end. Least is going to be furthest away from the end.
We have oxygen.
Furthest away is going to be fluorine, right? Oh, did I say nucleophilic or electron? Nucleophilic. Nucleophilic is the N. The further I am away from the N, the worse I am. The closer I am, the better I am. So fluorine is my least nucleophilic atom, and phosphorus/sulfur are going to be my best ones. Okay? And all that means, so think of it as acid-base rankings, right? There's going to be a lot of considerations that I have to keep in mind as I do this and as I rank, okay? So, but off the top of my head, automatically having a negative charge is better, okay? Negative charges, generally speaking, are gonna make everything a better nucleophile. So remember how in acid rankings, when we said, okay, resonance, generally speaking, is gonna be the defining factor in whether you're good or not. All right, same concept. If I have a negative charge, it's gonna automatically make me a better nucleophile. Now, in more extreme cases, will it? Probably, like if I'm comparing like this really, pretend I am doing like fluorine negative versus, I don't know, phosphorus. That might be a little more iffy. I don't think it's that iffy, but like there's some other considerations. For example, if I had a negative charge on an oxygen, but it was attached to like a giant thingy that would make it basically impossible to be a nucleophile, right? That would be pretty bad. But usually negative charge makes a good nucleophile. So let's go and look at our charges. Here I have a negative charge and a positive charge. Oxygen. Here I have the same structure, but with sulfur, also negative positive. Here I have negative positive. Here I do not have a negative charge or a positive charge. And here I do not have a negative charge or a positive charge.
With OH, we won't have negative positive for the last one?
No, because remember, this is a covalent bond,
Oh,
Yeah, it's true. Yeah.
right? So this is ionic. So when I dump my covalent bond into the solution, it's going to stay together. When I dump my ionic bond, it's going to break apart, right? So the middle three break apart, the ones on the right and the left do not. So automatically I know my bottom two, right? The ethanol and the one with the fluorine is going to be the least ranked ones because they do not have charge. Okay, and here I'm also dealing with 4 oxygens and a sulfur. And so the reason why I did that was for us to think through structures. The structures are very similar, instead we're thinking through atoms and the similarities between them. So the difference between them is here I have this. Okay, so what would the CF3 do to my structure and to my electron density?
are they both pulling? Both are electronegative.
Okay, so CF3 is inductive effect, right? Okay, so the fluorine is inductive effect. It's going to be pulling away my electron density away from the oxygen, okay? So, is that going to make my oxygen a better nucleophile or a worse nucleophile? If I'm pulling electron density away from the oxygen, it's going to make me better or worse?
Better.
Worse because nucleophile is negative.
Yes, okay? So, if this was an electrophile, right, if it's the thing getting attacked, would it make it better or worse? Right? Because here I'm evaluating electrophiles, right? So here, if I had something pulling away electron density, because I have an electrophile, it's going to make it better, right? Because I want that carbon that's being attacked to not have electron density, right? Because it's taking electrons. Here, I'm giving electrons. The nucleophile is giving electrons away. And so I want to pull, I don't want to pull electrons away from my nucleophile. I want that nucleophile to have as much electrons as possible in order to donate. Okay? So, inductive effect makes me worse. So this is going to be 5. This is going to be 4. Okay, so now I have 3 negatively charged ones. Alright, so first things first, I notice I have an oxygen with a negative charge, I have a sulfur with a negative charge, and then I have an oxygen with a negative charge and this giant thing attached to it. Alright, so let's talk through each of those elements. So, I have an oxygen and a sulfur. Which one's going to be better?
So oxygen
Oxygen.
is better. No,
Going
sulfur
down
is
the
better.
table, right? No, it's oxygen.
Sulfur will be better because going down.
Which one?
Sulfur will be better because, well, I think you said one time because it's larger, so it's
Polarizable?
yeah.
Yes. So that's the reason why. But also we just look at the beam chart, right? So the sulfur is going down, right? So sulfur is closer to the N on my beam chart, and therefore it's going to be a better nucleophile. The same way when we do acidity, basicity, all those things, right? So sulfur is going to be better. So let's just keep track. So sulfur is better than oxygen. Okay, and then what's better, big or small?
Small.
Small, right? So small better than big. So automatically I know which one's the third one. What is my least favorite one then?
So third one, the benzyl ring.
The one with the benzene ring is going to be number 3. Reason why is because I have something big attached to it, and it also is an oxygen, okay?
So you want something big attached to it?
You don't.
You don't.
You don't. 1 is best, sorry. 1 equals best.
Oh,
Sorry,
okay.
sorry. Yeah, so 1 is my best, right? And so when I have something big, remember, so think of it this way. If I'm shooting my arrow, my nucleophile is my arrow, what's going to be a better arrow? If I just have just my arrow, or if I attach a giant balloon to the back of my arrow.
Just an arrow.
Just an arrow, right? If I have a giant balloon, it's going to make it much harder to shoot my arrow.
Yeah.
So I want as little stuff attached to my arrow as possible, which is why the first, the second, and the third structures are the best. And so between oxygen and sulfur, which one's better?
Oxygen.
Which is the better nucleophile? Look at our chart.
Sulfur.
Look at our chart. This is sulfur.
Mhm.
This is oxygen. Which one's closer to my N?
Sulfur.
Sulfur. So which one's better?
Sulfur.
Sulfur, right?
But I thought you said you want it to be more negative. Always.
Yes. So what I meant by that was I want more electron density, right? And so for example, here and here, this oxygen is losing electron density that way. Here, it's got all its electron density. I also want a negative charge because negative charges indicate I have more electron density. But we need to consider polarizability, which is why sulfur is better than oxygen, because it has similar electron densities, but it's more polarizable because it's bigger.
So you want smaller, not bigger.
I want a smaller structure,
Yeah.
but a bigger atom is better usually
Okay.
for a nucleophile. And when we say bigger and smaller, this isn't a difference between fluorine and iodine where it's really, really big. Oxygen and sulfur aren't too big in difference, right? We're just talking about electron density. So sulfur is going to be better, and then oxygen is going to be second. 1, 2, 3, 4, 5. Questions, comments? Perfect. All right, so now it's time to do synthesis. Okay, this is going to be really fun. I had fun making this, so I hope you guys have fun doing it too. All right, so first of all, let's just talk about synthesis strategy, okay? When you do synthesis, they always usually have a giant thing and it's huge and it's scary. But what we need to do is we need to be very organized, okay? Like we were doing for Fisher projections, like Newman's, when you're organized, you're going to do better and you're going to make less mistakes, okay? And so, usually for synthesis, what they'll have you do is they might give you the end product and tell you to make it. In this case, it kind of does. All right, so let's just read the question first. All right, so the following synthesis scheme occurs when structure A is reacted with a reagent, 2 products Bmajor and Bminor are created. And then Bmajor is reacted with sodium hydroxide to create C, and C is S-but3N2-ol. And then C is reacted with sodium azide, maybe, N3 to create D. And then we want to fill in the missing pieces, okay? So there are some reagents that are missing, we have missing structures, and it just wants us to fill them all in, okay? Or I want us to, because I made it, but it is what it is. Okay, so this is gonna be pretty fun. We are given A, and we're gonna work with that. So far, we don't have that many reactions to work with, right? What reactions do we know how to make? SN2 and halogenation, right? Halogenation. Those are the 2 we know, and so as we go on and as we learn more OChem, our toolkit's gonna be even bigger, right? But now we know, because we only know 2, those are the ones that are gonna be used, right? I'm not gonna tell you all to do like E2, because we don't know how to do that. If you do, I can make questions for that, but I have to wait. So, alright, so first of all, let's just write down what we know, fill in what we don't know, and kind of make up what I call a reaction scheme, alright, the synthesis scheme. And it's just gonna keep us super organized. So A is reacted, and it gives me 2 products, Bmajor and Bminor.
Is the major minor is referring to the resonance major minor?
Maybe. We'll see. Okay, and Bmajor and minor is then Bmajor is reacted with NaOH to create C. And C is reacted with NaN3 to create D. Okay, so I need to know what this is, I need to know what this is, this. Oh, we know what C is. C is S-but3N2O. So I'm just gonna draw that in for us. It's gonna be butanol, so it's gonna be a butane. Which also makes sense because it started with a butane, I'm gonna end up with a butane, usually speaking, right? There isn't a way for me to magically add carbons yet. Okay, so I have, on my 3rd carbon, I have OH. No, I have an
The
alkene.
second.
Alright, on my 3rd carbon, I have a double bond. And my 2nd carbon, I have an alcohol.
Yeah.
And it's gonna be S, okay?
Mhm.
So S means 1, 2, 3. This is S. Wait, no, 1. No, this is 2. Sorry. This is 2, 3. This is gonna give me R, so the OH needs to be facing away from me.
Yeah.
Okay. So OH is gonna be on a dash. In order to get the S configuration. Okay, so I started out with an alkene. Somehow my double bond moves. I'm gonna somehow react this with sodium hydroxide to get an alcohol. What are we thinking we can do? What are some of the things in our toolkit?
It can only be moved by resonance, that's for sure.
Okay, so I know here somewhere I'm gonna get resonance. Right? And that would also indicate why I get a major and minor product. Right, and this also tells us major and minor. Okay. So, what are some reactions that we can do with a carbon without anything, right? So let's think, okay? I can do either, yes, right? So I can either do halogenation or SN2, okay? SN2 needs leaving group, no leaving group, right? So currently, does A have a leaving group that I can use? No, right? So therefore, it has to be halogenation. Right? Easy for us to know right now. In the future, when we have a lot of different reactions, we're gonna have to think about it a little more, but currently we only have 2, so we just use process of elimination. Okay? So if I have halogenation, then my reagents are gonna be, let me use blue for my fill-in. Okay, so my reagents are going to be bromine and light. Okay? Alright. So, if I brominate that, what is my B major and B minor?
So your B major would be the B minor would be the vinyl attachment, right?
What do you mean by vinyl?
Means like right with the double bond, it'll be the first, right?
Okay, let's think through this, okay? So, if I do this through halogenation, I have my hydrogen. The bromine's going to come with my radical and it's going to pull it out. And I'm going to get this. Right? And then now I'm going to get a resonating structure. And each of these are going to give me a different answer. Right? I can get this. So the question is, which one's the major, which one's the minor?
Is the major the
Or the
secondary one? The one on the left?
Secondary.
The secondary one, right? This is going to be major. This is going to be minor. No. Why is my secondary major?
It's specific.
Is it specified? Yes. Why is secondary better than primary?
Is it more stable?
Correct, right? Radicals, lack of electrons, so I want to be in a more stable position. Perfect. Okay, so let me fill that in real quick. Okay. Okay. So, somehow this is going to be reacted with sodium hydroxide to switch the oxygen, the bromine into an oxygen. So, what kind of reaction switches my stuff?
SN2.
SN2, right? SN2 will switch my stuff. This is going to be SN2 reaction. Okay, so all that's going to happen is oxygen is going to come in backside of attack, kick off the bromine, right? So now I get the alcohol. Okay. So I now have an alcohol that is stereospecific. All right. I kind of added that one in because I just want us to think about stereospecificity. I'm gonna not say that. I'm not gonna say that. Okay, but right. So now I'm gonna once again react it with something, and then that something is gonna be sodium. I believe it's azide. So all right. Here's a question. This is most likely gonna be another SN2, right? Because this is a good nucleophile. And then we're going to talk about knowing what reagent you're doing and all that stuff later. But we know this is SN2 because SN2 is the only thing we've done. So it's pretty simple. But later we'll talk about all the specifics. But I'm replacing my oxygen with my azide. So here's a question. Is alcohol a good leaving group? Or do I have to do something else?
Alcohol is not a good.
Alcohol is not a good leaving group, okay? So we actually have to do something to my substrate before I can do that. So what I'm going to do is I'm going to actually react it with tausyl chloride. And what that's going to do is going to give me this, OTS. Okay, so this is not a good leaving group. Need TSCl. Makes OH.
Is it the one the ground ether?
No, that's something else. Crown ether is something else. This is, I don't know the structure for it, but it's not a crown ether. Crown ether is something else.
So how do we write it? Just TSL?
Yeah, so TSCl is going to change oxygen into a good leaving group. And this is without changing stereochemistry. Okay, see look how it's on dash, it still stays on a dash. And then I'm going to now react it with NaN3, which is now going to react. Backside attack. And here is where I get my switch of stereochemistry. And I get this.
So for you get OTS. So for TSCl, TS is negative.
I'm not quite sure. It kind of like comes in. I'm not really sure of the structure, but
So
it's
we
kind of
will
like,
just join the oxide, like we take the H out and then join the TS with it.
yes, basically that's what it does, but it's a little more complicated than that.
Yeah.
It's like it has like a little benzene and it has some stuff attached to it, but basically it just turns that oxygen into a good leaving group.
Does it turn anything to a good leaving?
No, it only turns alcohols into good leaving groups.
And then this OTS will react with NaNH.
Yes, and then that will actually leave. So keep in mind also the OTS, this TS, the tosyl chloride, will not change my stereochemistry. So look how I started with dash, I ended up with dash. It's not until I react with NaN3 that I end up with inversion.
Makes sense.
Questions, comments?
Do we have time to do one more example?
Of this, of synthesis, it's
a lot.
I've only made one, mainly because it's kind of
So
intensive.
in the book we have, because I couldn't find for SN2, we have more?
You should. And if not, you can talk to your professor. But this is just an example of what a synthesis could look like. They usually take a while to make, so I don't know if I can just make one up on the spot. But we will have more, I promise. We're gonna get lots more synthesis. Synthesis is what makes OChem fun. So this will be fun. But this last synthesis question, I think we have one more reaction. Ooh, we're actually gonna finish the packet today. I'm happy. Okay, so it's pretty simple. We've done a bajillion of these already. Well, not a bajillion, but you know. All right. So again, I have my positive charged ionic bond. Carbon attacks chlorine. Chlorine leaves, and I get this. And I invert stereochemistry.
So what do solvent have to do with this? Like we were learning in class about the protic, aprotic. So aprotic is better.
Yes.
So does that solvent also count to determine if it's SN2 or not?
Usually it doesn't determine. Usually I don't think I've seen it. Usually it doesn't determine, but if you have a certain type, it'll be better. But that's all.
So it's better. So for exam, do we need to memorize all the aprotics or for especially like SN2 because we have a quiz next week? So I wanted to see if I have to memorize anything.
It will be good to know them. So I think like
just like kind of be familiar.
TMF is aprotic. I don't remember. There's like a list of like I think DMSO is aprotic. There's a couple like and aprotics are better. So like just all those. That's all you. Yeah, that's all you need. I don't think it'll be a determining factor. I've never seen it as a determining factor. But they might be like, if you're using aprotic, is that going to make your reagent faster, slower? That's kind of how they test that. That's how I've seen that in the past.
Makes sense.
But
And
yes.
for nucleophile, do we need to like know the list, like kind of memorize it, or just know it?
I would say you don't have to memorize it, but you need to be able to understand all the trends, right? You want a smaller nucleophile, and there's like some special nucleophiles that you just need to like know. But generally speaking, the nucleophiles are relatively straightforward. Just know the trends, right? Know what makes a good nucleophile. Know what makes a good electrophile. Know what makes SN2 faster, slower, all that stuff, and then you'll be good to go. and understand all this. So
Can we do this like in a Fisher? If we ask in a Fisher projection?
I haven't seen this being asked in a Fisher before, but if it does get asked in a Fisher, literally just draw it out. Draw it out into line angle and then go to Fisher. Like,
Because on Fisher they both are on.
wait, no, that's actually pretty easy, right? All you have to do is like
Just flip
V
it.
R and then let's say H
And
and then this is really ugly. Hold on. Okay, so like if we were to do a Fisher, it would be like I don't know, V R H H H, and then it would be like O minus CH3, and then it would just be like
Can they give us that?
oh, they can give you anything. But I mean, I've never seen anyone ask it in a Fisher, but if you were, I mean, it's pretty simple. You just switch, right?
of the suit.
Yeah.
And because I was thinking they both are the wedges, so how we would, because in Fisher
Ah.
it's
Yeah, because right. So all we need to do is switch, right? So if you're in line angle, you're switching from wedge to dash, right? If I were in Newman, I would just switch this and this, right? And then Fisher, I would switch this way. So I said that in terms of line angle. When you're switching in line angle, you always switch wedge to dash,
you
dash to
kind of
wedge.
change the chirality.
Yeah, all you need to do is, yes, that's basically what you do. You need to switch chirality from R to S.
Makes sense.
Questions, comments?
I'm thinking more.
Alright. That's all I have for today, mainly because y'all first class was only the test review, so I didn't have a lot to work with. But next week we will get into the full swing of things.